Okay, so this class is the first class in this semester, so I'm going to briefly introduce this course today. So this week we will spend maybe an hour or maybe an hour and a half to give you an overview of this course. So first of all, this is the syllabus of this class. This is the first week right here. And then you can see that we are going to spend about 3 weeks to talk about the principle of both fMRI. I assume not every one of you has the background about the MRI or the functional MRI. So basically, I will spend 1 week to show you how we acquired fMRI imaging and also what kind of the principle behind fMRI can help us to probe the brain dynamics or specifically the oxygenated related both signal. We will spend 1 week to talk about this point. And the next week, we will talk about the experimental design. For human study, experimental design is very, very important because what kind of a task you ask your participant or the patient to do will highly affect the result of the analysis. So experimental design is a key step for human study. But for animal study, it depends. Sometimes for animal MRI or fMRI, we may use a passive stimulus. You don't need to ask animal to do anything because it's very hard to ask the animal to do something for you. So you can use maybe the heat stimulus or some kind of the electric stimulus to induce brain activation in the animal. But anyway, it's still related to the experimental design. So we will spend 1 week to talk about how we can conduct an appropriate experimental design for the both fMRI. And in the first week, I will give you some general idea about the neuroanatomy because I don't think all of you have the specific neuroanatomy of our brain. And also, we will have the imaging atlas to help us decipher which brain region will involved in specific task. For example, motor task, cognitive task, or something else. So in this week, I will spend a little bit time, maybe 1 hour, in give you a general idea about the neuroanatomy. And in the second hour, I will let you use your laptop to do some imaging atlas. It's kind of the processing that we can automatically isolate or segment our brain into maybe 90 or maybe 100 regions. Different regions may involve in different functional tasks, for example, motor or something. So start from this week, March 12th, please bring your laptop. Before this week, you don't really need to bring your laptop. You can only just take the lecture. But then start from this week, we will have some hands-on and practice. Start from the first week right here. And on this specific day, March 19th, I have already booked 1 hour in our 3D MRI facility. We are going to have an experiment. We will actually acquire a set of fMRI data. So we can use this data set to do the fMRI analysis. So this week is particularly important. It will give you a general idea how we operate clinical MRI. Not for animal, but the clinical MRI. How we position our patient, and how we operate the console, the operation console, how we use the console to set up the parameters, and also how we deliver stimulus. This kind of the task design we mentioned in the third week. How we give, for example, the visual stimuli or auditory stimuli. How we let patient stay in such kind of the task condition, so we can really correlate their task performance to their cerebral hemodynamics. It's one point that we would like to do in the 5th week. So please reserve this date. If you really have something else to do, you may have something in these 4 weeks, but please, this particular day, please just keep your time right here. And unfortunately, I cannot book the exact time during 10 to 12 a.m., 10 to 12 o'clock a.m. because the schedule of our 3D MRI is pretty tight, pretty crazy in March. So I can only book this time duration. So please check whether you are available during this time. I hope you do. because it is very important. So if you cannot attend this 1 hour, please just let me know. So this is the 5th week right here. Please reserve the time. So we won't have the class during 10 to 12 on this specific day. We will have the class during 5 to 6 p.m. And please go to our 3D-MRI facility directly. Don't come to the class. Actually, we will go to, I think it is in the, it's in the second floor of the basement, but you can only enter the facility through the first floor of the basement. So we will find a place to meet up. Don't worry. I will tell you the specific meeting point in the 4th week. Then we will meet up in the 5th week. Okay. And start from the 6th week, we will go through many different, actually, 3 main categories of fMRI analysis approach. We will start from the image preprocessing. It is the essential step that no matter what kind of analysis you are going to do, you need to do the image preprocessing. If you have fMRI data on hand, this is the very first step you need to do. And in the 7th and 8th week, we will show you how to perform so-called GLM, General Linear Model, to identify which specific region may involve in so-called brain activation for a task, such as the motor task or something else. We will separate this topic into 2 weeks right here, part 1 and part 2. So this is the 7th and 8th week. And about the 9th week, I intend to talk about the amplitude of low frequency fluctuation. It's kind of the analysis that focusing on the frequency pattern, not simply the time series pattern, but the frequency pattern. This is a particular way I'd like to introduce in the 9th week. And in the 10th and 11th weeks, I will talk about brain decoding. It involves a technique we call the multivariate pattern analysis. Multivariate pattern analysis is an approach that we will consider whole bunches of voxels, not a single voxel, but whole bunches of voxels. They may connect it with each other or in a neighborhood, but it can also distribute in very different brain regions. But we can use this kind of multivariate pattern analysis to help us decode how our brain represents the information that we send to this participant. For example, if we show a picture, a cat picture or a dog picture, how our visual cortex will encode this kind of visual stimuli in our brain. So we call multivariate pattern analysis is one of the methods to help us to do the brain decoding. So again, we will spend 2 weeks to do so, part 1 and part 2, right here. And start from the 12th week, I think the May 7th, I will start talking about the brain network. Brain network is a general term. Actually, it involves the functional connectivity, maybe effective connectivity, and even the graph analysis or graph theory. It's a very huge topic right here. So actually, we will expand this brain network topic into, I think, 5 weeks right here. And there is another specific day, May 14th. We have no class in this week because I'm going to attend the ISMI annual meeting right here. So there's no class. You don't need to come to the classroom, okay? There's no class right here. And then finally, if we don't have too many students, we may only spend 1 week to do the final report. As I mentioned earlier, you can either pick the topics that you are currently doing during your graduate study or something. Otherwise, if you are not really involved in some kind of the fMRI study, you can simply pick 1 or 2 literatures. You can simply just review the literature and help your classmates know what is the current studies of the fMRI right now. So this week, I think it depends on finally how many students will take this class. If more than 10, then we may need to spend 2 weeks on the final report. It depends on how many students. So we will decide this or maybe change this syllabus after this or next week. I will let you know the most updated syllabus. Okay. You can find all the teaching materials on my website. Here is the linkage right here. Okay, and this is my website, CF Lu. It's my Chinese name, Chia-Feng, okay, and then again the address of my website, and then you can find there is a button called Contents right here. You can just press the button and you will see there is a pop-up menu right here. Just pick the teaching materials, and then you will find out specific course that named as fMRI analysis right here for graduated student. And once you click this button, you will have the full link like this. So this is a way that you can find all the handout. Even today, I have already uploaded it to my website, so you can download the PDF file, the handout, into your notebook or computer, so you can easily follow the lectures, and even if you want to do any review or take notes, it's pretty fine. And also, if we have some data, the data for you to practice the analysis approach, I will also put on this website, so you can also download the materials right there. Here's the rule for this class. This is how we evaluate your performance. First one is attendance, and I think this is the minimum requirement based on the student law that at least 1/3 lectures you should attend. But since this is one of the hands-on course, try to let yourself participate in this class. It will definitely help you. Okay, so this is the participation of this class. And finally, the final report. As I mentioned, that either literature or either your own works that will be fine, but it will occupy the most of the points right here, 50% right here. The previous slides is trying to give you a general idea how we will perceive this class in this semester. So is there any questions right here? So in the following slides, I'm going to give you an overview. Before you do any analysis, you need to think about what kind of questions you are going to ask. Or you can say what kind of answers you are seeking for to a specific question. Okay. For example, if you aim to use fMRI, functional MRI, to determine what kind of brain activation to the corresponding task. For example, if I ask my participant or patient to do the motor task, such as the hand grasping right here, which brain location, which brain region will activate responding to this kind of the motor task? This is a specific question I'd like to ask. So you can just change the task. Either you change the motor task to the language task, or heat stimulus, or anything. But which specific brain region will activate in response to this kind of task? This is the first key question. If you are seeking for a specific location, you want to investigate the brain activation, this is the very first question for you. But if you are not interested in this one, you intend to ask another question. If I give a specific stimulus to the subject or to the participant, for example, a picture of cat, a picture of dog, a picture of human face. In these three different stimuli, what kind of brain representation? Representation means how our brain encode or decipher or record this kind of information into our brain. How can our brain differentiate these three different stimuli? This is kind of the issue that we'd like to ask. So this is more like the brain encoding. Both three categories, cat, dog, and human face, are visual stimuli. We always show the pictures right there. But our brain can still differentiate, this is the human face, this is a dog, this is a cat. So you definitely have a specific way or encoding pattern in our brain to help us differentiate these kind of things. So if you are aiming to ask, can our brain really differentiate or really tell the difference about the task or the stimuli? This is the key question you'd like to ask, brain coding. And the final one, from the early 20th centuries to late 20th centuries, people tend to believe that our brain is not working as individuals, but also working as a network. That means our brain regions may collaborate with each other. When we do specific tasks, like even the motor task, not simply the primary motor cortex will be activated, but also some regions like the supplementary motor area or region like the parietal lobes is kind of the region that help us to integrate the information from the sensory to the motor or something. So we tend to believe that brain is kind of a network, just like the computer network. Our brain is a very complex organ in our body, and it just works like a network. The brain regions will collaborate with each other or coupled with each other to fulfill very, very difficult or very complex tasks right there. So in this topic, we will ask brain connectivity. Connectivity is a specific term that transfers from the connection. Actually, how our brain connected with each other to fulfill a very difficult task or complex task. This is the way we'd like to ask. So actually, I simply just divide all the questions into these three different categories right here: brain activation, brain encoding, and brain connectivity. For each specific questions, you will use different analysis techniques right there. You are not going to use the same analysis way to answer all the questions. It's not gonna happen. So all you need to do first, you need to identify which one is your key question. Then you seek for the appropriate analysis technique to do so. Right, specialization means each brain region may specialize for a task, either motor, either sensory, or something else. This is the early idea about our brain. There is a very famous atlas called the Broman Atlas or Broman area that used the histology information to help us to separate or categorize the brain into with very specific boundaries that you can tell this is the region of, just like a nation. With other nations, they have a border. Very clear definition about different regions. This is called specialization. But actually, our brain is so complex. Sometimes you need to think about pattern, but not a single point. But I think it's just used to probe different questions right here. If you are going to ask the question, where is the motion area? You need brain activation. If you are going to say, where is the face recognition area? To differentiate this angry face, it is a neutral face, or this is a happy face or something, or either to differentiate this is a human face or it's a cat face or animal face. Then there is a specific region, I think it is in the temporal lobe or something. This is a specific region or area that is response to the motion or face recognition. It's called brain activation. But when you are going to ask this kind of question, what are the varying brain states in an area? That means an area can be very different. I mean, the activation level can be very different to different stimuli. For example, the cat or the dog pictures are very different. So in this way, we can only say that this region is highly associated with the motion or motor task or something. But in this question, we will say this area have multiple tasks or multiple functions. In this kind of situation, it will come in. It will have a very high activation, but in another situation, it will come down. So this kind of the issue is we call it some freedom to each area. You will have the multiple purpose or multiple functions even for an area right here. And how do brain cortex encode different types of information is a key question. For example, how can we use fMRI to tell whether the subject is telling a lie? He said, I'm not a murderer. I didn't kill anyone. But actually, his brain pattern is telling that he is a liar. He actually murdered or killed someone. This is a way that we say is maybe just a lie detector, or it is the way that we can decipher how our brain works or how our brain represents the information. So this is pretty different question. You kill the location right here, but here you kill the pattern. Okay. And the final one, how do neurons and neural networks process information or collaborate with each other? How can they work as a team, as a network to fulfill a very complicated task? So actually, three key terms right here for your reference. The first one, specialization for the brain activation, representation for brain encoding, And the final one, integration, is the word to describe the brain connectivity. Okay, so if you're going to have an fMRI study, or your professor or supervisor is going to ask you to take one of the experiments. Maybe it will be your thesis, or you need to publish some paper about this topic. Just think about which topic you're going to really dig in, or you're really going to do. Okay. Let me transfer all the text into the figures. I think it may be better for you to understand what I'm going to do in this semester. First of all, I think this is the body signal. Don't worry about this. I will spend 1 to 2 weeks to let you understand how we acquire this kind of fMRI imaging and how we acquire so-called body signals right there. Body signal is just a measure that we can actually acquire the profile of the hemodynamics of our brain. But actually, this hemodynamics is highly related to the oxygenation level in our cortex. So this is just different profiles from different locations. For example, you have a time series or time course body signals right there come from the medial prefrontal cortex or something. And also you may have another one from the maybe posterior cingulate cortex. It's just another brain location. You will see the profile is very different. So what can we do if we have these body signals on hand? Basically, 3 categories, just like I mentioned in the last slide. First one, you can ask whether the body signal will change as you ask the participant to do specific tasks. For example, we can design a so-called block design. In this kind of block design, in this color, we will ask the participant to just take a rest. You don't need to do anything. Just relax yourself, and maybe you need to stare at a white cross on the screen, but you don't need to do any motor task. You just relax yourself and don't move. Very important thing, don't move your head, okay? And in this kind of color, these blocks, we will ask the subject to do, for example, the hand grasping. So you will anticipate if there is a brain region that's really involved in this kind of a motor task, the body signal may have a specific pattern right here. It's just like the profiles that will go up when the subject is doing the motor task and coming down when the subject is resting. Okay. So this kind of a change, this kind of a time course is the hint or is the feature that we are seeking for. If we can identify specific voxels or brain region exhibiting this kind of the profiles, I would say these brain regions is highly involved for this. This is the first idea. We try to use some statistical analysis. Actually, we try to identify the similarity between local body signal is the local time profiles and the task design. If I can identify high similarity between a specific location and the task design, then I will say this is the location of the brain activation. This is the very first part. And the second one is the brain activity pattern or so-called brain encoding. This is the issue that we try to classify or identify the similarity analysis between different conditions or between different stimuli. For example, I let the subject to see a black cat and a dog. Even in the same brain regions right here, the primary visual cortex or somewhere, I just take an example right here. You can see they may involve maybe right here 16 different voxels. And you can see when the subject is looking at a cat, the pattern is more like this one. The upper region may have a higher, that means a more red one, high activation right here. But within this identical 16 voxels right here, for the dog pictures, you will see the activation will more located in the left portion right here. So this is a different pattern, even in the same brain region, but different pattern right there. So nowadays, when people try to really decipher or try to really understand how our brain will respond to different conditions or different stimuli, this kind of a pattern is a key features that you'd like to use to differentiate these two different issues. It's just more like when you are talking about the machine learning, you definitely need some features to let your machine to learn from. So this is the pattern, this is the features that the machine can be used to learn. So actually, brain encoding is a technique that highly involves the machine learning. Actually, you will learn this during this semester. But this one, machine learning may not play any role in this one. You simply need the general statistical approach, so-called general linear modeling. Then you can answer the brain activation, which is the specific rotation you are seeking for. And the third category is the brain connectivity. In this situation, we are investigating the dependencies of both signals. Again, the profiles, the time course profiles between brain regions. If there are two brain regions have high correlated or high similarity both signals, then we will say these two distinct brain regions may collaborate with each other to fulfill this kind of task. So actually in the brain connectivity, we are measuring the statistical similarity between brain regions, of course based on the both signals. Right? So I take this as an example that we may have the two motor region. You don't need to care about very little words right here. Just look at the profile right here. The blue curve and the red curve may come from different hemispheres, one from the left motor region, one from the right motor regions. But you can definitely tell that these two profiles is pretty similar with each other. So I would say even the signal come from different brain hemispheres, they still have a high we can, based on this point, actually to build up a very complex brain network right here. We can really calculate the similarity between just each pair of the regions within your brain. So if you have, for example, 100 different brain regions, you can estimate the correlation between just each pair of them. So you will get, I think it's over 6,000 connections you can actually measure. So it's three categories that I intend to display or present in figures, so it may be better to help you understand what we are going to do. So in the following slides, I will use maybe 2 or 3 slides for each topic, so you will have a general idea. I say this is simply an overview. I will spend the whole semester to help you understand how can you perform this kind of analysis. Okay. So very first step. No matter which category, which question you are going to ask, both fMRI preprocessing is essential step. No matter which one, you definitely need to do the both fMRI preprocessing. Although not every step in this flowchart is mandatory. Actually, the smoothing is not a mandatory one for, specifically, it's more like the forbidden step for the brain coding analysis. Actually, you cannot do this smoothing process to your fMRI imaging. If you are intending to do the brain coding analysis, you cannot do this one. But for brain activation, you need this full chart. And when you consider the brain connectivity analysis, this one may be yes or no. It's kind of the optional one you can test whether this one can give you an extra benefit or not. You can just try to do this. And sorry, I may forget to say on the next slide, I think. For the preprocessing step, I will use the SBM, actually the version 12, to do all the analysis. Different step will try to correct or try to improve the image quality into a certain level. For example, the first one is trying to correct the time difference. Actually, the imaging acquisition time difference between each slide. So we call it slide timing. Actually, there is a very slight difference, I think around 10 millisecond difference between each slide. So we need to actually correct for this slight time difference because it will definitely affect the temporal profile of our both signals. So we need to do the step. The 11th step is to help us to correct the head motion. Actually, the participant or the subject will lie on the table and the MRI table for, I think, at least 6 to maybe 15 minutes. It's a pretty long time. So normally, if you are a living person, it's really hard for you just keep your head totally unmoved. It's kind of an impossible mission. So actually, we will use realignment step to correct the motion artifact. Actually, we realign all the images from different time points to the first one to ensure that the brain are in the same coordinates. And then the co-registration. This is a step that we are going to register our fMRI imaging into a high resolution, high signal intensity, or high signal quality anatomical imaging. That is called T1 weighted imaging. This is very important because for the fMRI, we need to sacrifice some spatial resolution for the temporal resolution. So we can really measure the temporal profile. However, this sacrifice the spatial resolution can be regained if we co-register our functional imaging to the anatomical imaging. So we will perform this co-registration step so we can have a very clear and high resolution anatomical information. And this one, normalization, is a step that we try to sometimes change or modulate or just try to make everyone's head with a very similar size and shape. It's a step that we transfer each one's head to a global coordinate or unified coordinate. So I can really say that in this brain region, everyone has the same location right there. This is the so-called spatial normalization, not signal intensity normalization, but spatial normalization. And the final one, smoothing. It will reduce the spatial resolution further, but it will help us to improve the signal-noise ratio. It is a key step for reduce the noise interference. I will introduce this in one of the weeks, so don't worry about it. During this semester, I will focus on MATLAB. I want to use another interface like the Linux system. Some of you may know that FreeServer FSL is some other choice that is very useful and very helpful when you intend to do the fMRI analysis. But it will make this class become too complex. So I will focus on MATLAB. I will find all the toolbox that basically implanted on the MATLAB interface. I will do so. Okay, but it doesn't mean that only MATLAB that you can use for the fMRI analysis. It's just one of the options, but to me it's pretty handy, pretty useful. So I think it's just the way that you can learn. If you are the beginner, you don't know anything about fMRI, I think MATLAB is a pretty good option right there. So for each topic right here, brain activation, brain decoding, and brain connectivity, we will have several different techniques right there. General linear model for brain activation, MVPA, multivariate pattern analysis, or even there is I think the modified approach we call the pattern similarity analysis. It's also derived from the multivariate pattern analysis, but it is a different way to analyze your data or to interpret your data, I think. So I think this is two main techniques that you will learn during those 2 weeks for the brain decoding. And for brain connectivity, there are so many different ways. So we will spend 5 weeks in this topic. From very simple functional connectivity, it's more like the Pearson correlation coefficient. It's pretty simple one. And then we will go to such as the independent component analysis and go to the graph theory. It's a kind of the complex, it's just choose a complex way to quantify, to summarize your brain network. For example, how efficient your brain network is. For example, if I pick 2 subjects, I intend to say maybe this brain is more efficient than another one. How can I give this kind of a quantitative number or value to say you are really more efficient than others? We have an approach called graph theory or topological analysis. It is a way that we can quantitatively summarize our brain network: efficient, resilience, clustering, coefficient, and so forth, so on. This is many different ways that we can really tell how our brain work or how our brain integrated with each other. So I think there are so many different techniques that you are going to learn in this semester. But again, all based on the MATLAB interface. So for the very first topic, the brain activation, I just take this this experimental design as an example. This is a very simple block design. Actually, when subjects see this kind of the resting picture right here, you don't need to do anything. But once the video becomes to do the hand grasping right there, you need to do exactly the same thing with the video. You just need to do the same thing. Okay. This is kind of a block design that originally you don't need to do anything. That's called the resting period. And then in this period, we called task period right there. And wait another 20 seconds, you will see now it's come to the rest period right here again. And then another 20 seconds, it definitely will become the task period again. So this is called block design because each task is just like a block right there. Okay. So we will actually repeat this kind of a hand grasping task for 10 blocks. Okay. And during this imaging, we aim to identify a region who will have the bullet signal highly correlated to this kind of block design. I say we are trying to identify, or we are trying to assess the similarity between bullet signal and our experimental design. So you can see right here the primary motor task, which is definitely involved in this right hand motor task in the left hemisphere primary motor cortex right there. You can see the bullet signal profile is actually, you can count actually 10 waves right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just all happened simultaneously with this block design right here. So I would say, yes, this region may highly correlated to this motor task. But another region, right here, the visual cortex, also you will have a very similar profile. Why? Because you use the video, you use the visual stimuli to your participant. So when you see the resting picture right here, and then when you see the moving video right there, I think the brain will get different visual stimuli, right? So you will have these two different regions have very similar profiles that similar to your block design right here. So this is the very simple way that we conduct the fMRI, and it can help us not only identify the specific brain region, we call brain activation region, but also you can use this one to do so-called brain connectivity analysis. I'd like to know when this region has this kind of a bullet signal profile, is there any other region may have the similar profile with this one? For example, the visual cortex. So I may say this task can only be accomplished when subject first seeing the video and then give the order to the primary motor cortex to do the hand grasping. Okay, so this is another way to interpret how our brain helps us to finish this kind of motor task. Of course, we will use the SPM since we are using the MATLAB. And based on the GLM, general linear model analysis, you will definitely have this kind of the images on hand. You definitely will need some t-test or f-test, but you will have this kind of the activation map on hand. This will help us to really identify this is the cerebellum region, this is the posterior, more like the occipital lobe right there. So this is the region that we call primary visual cortex right here. And also you will see there is a region we call primary motor area. And actually primary motor area is a very long area, but for the lateral part, it's highly involved in the your hand or finger motions right there. So you can see this kind of map with bright yellow or red color right there. I would say this is the brain activation location right there. But if you see no color encoding, only the cortex, then there is no brain activation was identified in this region. So this is the very first part that we will conduct a simple experiment, and we will see what kind of this. For the students that you may involved in animal studies, normally when we deal with the animal fMRI, I think the racing state analysis or the brain cognitive analysis is one of my best choice anyway. But you can also use some heat stimulus or electric stimulus to your animal, for example, rat, normally rat. Then you can also conduct the blood design. Actually, just put the rat in the racing state, then give some heat stimulus right there, and also come to the rest state. So you can just have the very similar profile, but of course in a different brain regions right there. And also when you are using the animal model, you can also give more challenging tasks like the oxygen or CO2 challenge. You cannot ask a human being to inhale the CO2, but you can let your rat or animal to do so. So it's just one of the ways that you can study the physiological response to some kind of a crude state anyway. Okay, this is the second part that we called decoding activity pattern of brain. As I mentioned before, that now we are not really focused on the brain region, but focused on the pattern. We're looking at the pattern of activation within a brain region, actually just within a brain region or few brain regions, to answer or to differentiate what kind of the stimulus or condition that a participant is in. It's kind of the question we are asking for. So this kind of the multivariate pattern analysis is actually a classification problem. When we say classification, it's definitely related to the machine learning. We can use machine learning, and we can use the Foxo activation pattern as the feature. Then we can do the classification, right? Definitely, you need a sufficient sample size to train your machine, but eventually, you will have a machine that can help you differentiate what kind of state or it's truth or lie or anything. When we are talking about the classification, we definitely need a example. This example is our fMRI data. We can imaging our subject for several different runs or several different times, and these are the examples, just the data set, okay? And the features is the pattern that I mentioned before. You can use the fMRI, Foxo intensity or Foxo activation pattern as the features. So machine can learn from this feature. Then you need to pick the right algorithm, for example, support vector machine. I think in this MVP analysis, support vector machine is still the best option for you, not deep learning, because deep learning architecture need a very huge sample size. But for SVM, I think it did a pretty good job. For many literatures that involved in MVP analysis, SVM always give you a very high accuracy, around maybe 85 to over 90 accuracy. So I think pick a right algorithm to help you classify the brain state based on the features is a way you understand how our brain represents the different classes right there. I'll take this diagram as an example right here. For example, you let the subject see two different pictures. First one is the bottle, another one is the shoe. Of course, you'd like to simply use the brain activation pattern to say whether the subject is looking at the bottle or shoe. It's just kind of the prediction. You don't know what the picture he is really looking at, but you try to answer this question or predict this question based on the brain activation pattern. We can pick 6 different functions right here. So V1 for Foxo 1, V2, V3, V4, V5, V6. It can come from different brain regions. It's not necessary to within the same neighborhood. It's not necessary to do so. You can just pick different Foxos from different brain area, and then you use the maybe the signal intensity or the activation level from these 6 Foxos to become a feature factor. So it's more like a 6 by 1 factor right here. When the subject is looking at a bottle, then you will see, oh, for 3 rounds right here, 3 measurements right here, or each block anyway. You can see that factor 1, factor 4, 5, 6 always have a maybe darker factor label right here, like a grade 1 or something. They may be a little bit different between each other, but you can see that they have a similar pattern. That normally factor 2 and 3 will be brighter and the others will be darker. But when subject is looking at a shoe, you will see that factor 2 and 3 will become darker, but the other will become brighter. So this is kind of the pattern or feature set. Now you send this feature set to, for example, the SVM. Can we use this data to train SVM, support vector machine, to help us find the proper boundary right here? So next time, when we have a new data set right here, actually you don't know which kind of the imaging the subject is looking at. You only have the data right here. If I send all the data into this machine, can the machine help me to determine? Actually, this pattern is more like this one. So the subject is looking at the shoe. And also this pattern is more like the bottle. So even you randomize the order, the stimulus order, it doesn't matter, because now we are going to determine the brain state or the image you are looking at solely based on the feature set. I mean the intensity or activation level from 6 factor. So this is the general idea. We now no more care about the similarity between the factor body signal with the task design. We now care more about whether one specific condition or one specific stimulus can induce a specific pattern in your brain. Now, this is what we are talking about. So this is the general diagram. I hope this diagram gives you a general idea about what MVPA is going to do. Finally, the brain connectivity. Actually, when we are talking about the brain connectivity, there are several different categories within this topic. Structural connectivity, functional connectivity, and effective connectivity. Structural connectivity, that means you can really, for example, in MRI, we use diffusion tensor imaging. We can do so-called stratigraphy. That means we can really visualize. I think this is the major of the Professor Lin, that they can use a stratigraphy to actually connect 2 different regions through different pixels. We call this is a stratigraphy. And of course, stratigraphy has several different approaches, like the deterministic one or a probabilistic one. But in this way, I just try to show you the general idea that you can really see the lines through different brain regions. We call this is more like the neuronal fibers. Okay. And these fibers, we will say this is more like the anatomical links or structural connectivity. I can really say from one specific thalamic nuclei, whether this kind of thalamic nuclei will project to, for example, the parietal region may be more like the somatosensory regions. So I can say these thalamic nuclei may highly corresponding to the sensory or motor task or something. This is so-called structural connectivity or structural connections. And for the functional connectivity, we can use multiple measurements to estimate the functional connectivity. The very first one, definitely the fMRI. But if you have the chance to see the data from EEG or the MEG, I think you still can use this temporal profile to do the functional connectivity. It's not really limited to the fMRI, but you can use other techniques that can provide sufficient temporal information, and you can also do the functional connectivity. So functional connectivity is more like something unreal. You cannot really see it, but you simply estimate the statistical dependence between two areas, 2 channels, or 2 different places. It's just the idea about the functional connectivity. So in functional connectivity, we usually present the data in this way, just like we called node and bar, just like nodes and the bar, or sometimes hub and the bars or something. This is the way we present the functional connectivity. And the final one is the effective connectivity. in this specific question, we now not only want to know the correlation between two brain regions, I also want to know the causality. Who is the boss? Who is the leader? Who gives the order to do the task or something? So I want to know if there are two regions are highly correlated with each other. For example, region A and region B. In this functional cognitivity, I would simply say they may have a correlation coefficient larger than 0.6. That means a high correlation coefficient. Okay. But in this question, I would say not only I'd like to know A and B is correlated with each other, but I want to know maybe A cause B activated. This is another question. It's more like the causal interaction. I'd like to know who is the boss, who is the higher level, and who is the lower level. And definitely in this effective connectivity, the question or the analysis becomes very, very complex, because now not only the correlation analysis you need to use, but also the directional analysis you need to know. So it's kind of the very complex model that normally you don't want to analyze regions more than, I think, more than 10 is too much. Maybe 5 is appropriate region number. 5 regions you can determine the causal interaction between these 5 regions. But if you try to determine the causal interactions between 10 regions, it becomes very difficult. Now, to the 100 regions is kind of impossible. I think even you can get a result, the result is very hard to interpret. And it's also very hard to believe that the result is real. So basically, effective connectivity, if you want to use this kind of analysis approach, it highly depends on whether you have a specific model on your hand. For example, I simply want to know the primary visual cortex and the parietal region, what kind of a relationship between them. For example, if the primary visual cortex receives the visual stimuli signal right there, well, this region transfer or send a message to the parietal region to conduct the subsequent So if you have a specific region or specific model, then you can use effective connectivity. But for first two, it's kind of the whole brain-wide analysis. You don't need to focus on simple 1 or 2 or 5 regions. You can just put all the brain regions, 100 regions, into this kind of a structural and functional connectivity analysis. As I mentioned before, that functional connectivity is simply a statistical association or dependency between 2 or more anatomically distinct regions. So I already took this as an example before, that we can just pick different hemisphere motor regions right there. You can see the temporal profile, the both signals are pretty similar with each other. And now, when the patient is in a so-called resting state, you can now pick maybe 4 different regions. From this one should be the medial prefrontal cortex. This one may be the posterior cingulate cortex, and maybe one from the superior parietal region and one from the inferior temporal gyrus. There are 4 different regions, and you can see, again, the profile is pretty similar with each other. Actually, they can become a network we call deform network. That means even you instruct, you let your patient do nothing during scanning, your brain still have a specific network we call deform network. That means you are not really shut down. You are not a machine just shut down. Actually, you are in a state that we call the resting state, and this state will highly involve the deform network. This network will specifically help you to do the self-referential, will help you to memorize what was happened before, and what you're going to do is more like the state that going inside yourself is called self-referential state. I think functional connectivity is the way that we can identify whether several regions can collaborate with each other to form a network, so-called motor network between these 2 hemispheres, deform network during the resting state. It is kind of the statistical way we can do. And if we would like to really construct a brain network, I mean very complex brain network, maybe we need 100 different or maybe 116 different brain regions, and then we will estimate the functional connectivity between each pair of the regions. The very first step, we need to postulate. Postulate means segment or separate our brain into several different regions. So this is the original T1 weighted MRI imaging. That means these are anatomical images actually. And we can perform some kind of the normalization and segmentation and finally overlay our imaging with a template. This template, sometimes we may call it atlas. Then we can obtain so-called individual atlas. This is one of the 3D model that you can see different brain regions have already labeled in different colors right there. Or you can see the actual slides right here. Now you can see different cortex will be assigned into, for example, this one is a superior frontal gyrus in the left hemisphere. This one may be inferior frontal gyrus, and this one may be the insular, left insular or something. So you can actually use the analysis flow chart to do this so-called brain postulation or brain atlasing. Really postulate brain regions into over 100 regions, so you can tell the difference of the brain. Once you have this kind of brain atlas, now you can estimate the both signal between different brain regions. The both signal will be calculated as the average both signal within the brain regions. A brain region may cover maybe 100 or 1,000 voxels. Each voxel will have its own both signal. But now, when we estimate the regional both signal, we will simply average the both signal across all voxels within one brain region. And then we can calculate the Pearson correlation coefficient, the similarity between brain regions. So we can have this kind of the plan right here. I simply take this experiment result as an example. For the upper row right here, this is the data acquired from the healthy controls. And the lower row right here, this is the data acquired from the mild traumatic brain injury patient, just like the concussion patient. Okay. Even concussion is kind of the disease, or normally it's just treated like an event that you are riding your motorcycle, wearing the motorcycle helmet, but suddenly the taxi in front of you just suddenly stopped. You cannot brake in very short time, then you just hit on the taxi. It may have an impact on your brain, and sometimes with a helmet, you won't have the contusion or the brain bleeding. You won't have this kind of situation. This kind of situation we call concussion. That means no obvious brain damage, but you may still have so-called post-concussion symptoms. This kind of symptoms is pretty annoying because this may interrupt your sleep. You may have the sleep disorder. It may retard your memory function. It may make you become easy to be angry. It may be depression, anxiety, or something else. You have a whole bunch of diverse symptoms after concussion. But there is no evidence that we can really say this is a disease, because normally when you use computed tomography CT or you use conventional anatomical MRI, you cannot tell is there any structural deficit in your brain. No, there's no. That's why this is called concussion, not contusion. But actually, when you use the functional connectivity analysis right here, it's very easy for you to compare the upper row and the lower row right here. You can see the connections in healthy controls is pretty substantial. There are many connections between brain regions. But for a mild traumatic brain injury patient, the connection becomes pretty low or vanished, disappeared. That means the connectivity structure has already been disrupted or changed. And this may be the reason why the patient have the symptoms. But this is kind of a hidden information that you can only dig out using functional connectivity analysis, not using the traditional way. So this is just one of the examples. You can do the whole brain function connectivity. You may see this kind of a general picture right there. And the final one, I mentioned that we can use so-called graph theory or so-called topological properties to summarize our brain or to quantitatively summarize our brain. Very first step, you need to construct a network. That means you need the cortical region or brain regions. We will say this will become the nodes. And then you need the edges The edges is more like either the functional connectivity, just that we mentioned before, or you can use the fiber connection, just like what I mentioned, the topography, the neuronal fiber connection between different regions. With nodes and edges, you can have a brain network on hand. And then we can use so-called graph theory to really quantitatively measure how our brain how our brain connected with each other. And is it an efficient network or is it a compact network? You can answer this kind of question. Our brain networks or any network in this world always suffering this trade-off. Actually, wiring cost and efficiency. Wiring cost, that means if we take the anatomic connectivity, for example, that means how many neuronal fibers you need to fully connect your brain. It can be a very huge number if you really want any of the two brains in your any of the two regions in your brains will be directly connected with each other. You definitely need a whole bunches of the fibers connected with each other. And it's not going to happen because there is limited space in your brain, so it's not going to happen. We call it wiring cost. Another one is efficiency. If I don't have sufficient connection, fiber connection between brain regions, how can these two brain regions efficiently connected with each other or efficiently communicated with each other? That would be another problem. So this kind of a trade-off. If you want to spend more wiring cost, high wiring cost definitely may give you high efficiency. However, the cost is too high that normally our brain cannot support this kind of a situation. So we need to find a beautiful balance. There is a balance point between these two kinds of situations. So this one we call lattice topology. Lattice topology is more like a regular connection. So you can see the wiring is more like the connection only between the single node and its neighbors. So only these two. You don't have the long connections between the two nodes separated too far from each other. You can only have a short connection with your neighbors right here. You can see, yeah, this kind of the wiring is pretty simple. The cost is pretty low. However, the efficiency is also very bad. Why? If you want to send a message, send a neuronal signal from this node, from frontal region to your occipital lobe, you need to take so many steps. You don't have the one step, you don't have one quick way or shortcut from this point to this point. So this one, you have very low cost, but also you have a very, very bad efficiency in your brain. Another one we call random topology. Any two of the nodes or any two of the brain regions will randomly connected in your brain. So you cannot anticipate the pattern. Everyone will be different. Everyone will be so different with each other because it's kind of a random process right there. But the good thing is, normally, if you have a random topology, you have a very high efficiency because any two region will have a certain probability to connect it with each other. Even you don't have a very good connection directly between these two regions, you may find another node or another two node will help you to transfer from this point to another point. So random topology is the brain network structure that will cost you a lot because you may spend so many wiring, so many fibers between any two regions. But the good thing is the efficiency will be very, very high. However, again, it is not going to happen in your brain because our space is limited, the energy is limited, nothing will happen like this. So our brain is actually in this kind of a situation, complex topology. We call complex because this is a nature state that between these two states. It can have a very good balance that you have sufficient efficiency, but sufficient low wiring cost. It's kind of the very elegant brain network that we have. Actually, this has a special name we call small world architecture. Why we say small world? Because this is a very the term it comes from a very early experiment. It's kind of the social experiment. Actually, they send a mail the real mail, not email. Let's send a mail from maybe the east coast of the America to the west coast of America. And try to figure out if I want to know someone that I never knew before, I want to send a mail to someone in another way. How many people that I need to go through? For example, I know one of the students, but I guess maybe this student may know the person I'd really like to know, the person I really want to send the mail to him or to her. So I picked this one. Then he said, well, I get the letter, but I get the mail, but actually I don't know this one. However, I have my friends, and I think maybe one of them have a better chance to send the mail to her, okay, or to him. Again, he just transferred the mail to another one. So how many steps will this mail go through to finally go to his final destination? Actually, during very early time, I think it's just 1980 or 1970 or something, it cost 6. We call 6 separation. But nowadays, when we have Facebook or Twitter like this separation is shortened. I think it become 2.7 or 3.6. There is the new social experiment to verify this point. But anyway, after this kind of a social experiment, people tend to believe that actually this world is pretty small, because you only need to spend just 6 to transfer, and you can just find anyone you want to know. Okay, but nowadays I believe it's just 1 separation. If you really want to say something to Trump, you simply need to post on his Facebook. So this small world architecture is the elegant way that our brain preserved and to have, so we can really have a high efficiency, but also a sufficient low cost in our brain. And finally, I'm going to introduce the graph theory. Graph theory is an approach that we try to use several values or several measurements to summarize a graph. And in this case, the graph is a brain network. We try to use several measurements, for example, degree, strength, crossing coefficient, and path length, or so-called separation, to summarize the performance of this brain network, or for a single node, either way. So degree is defined as the number of neighbors. If we take the node 9 as the example, I would say this node is connected with 8, 1, 2, and 3 nodes. So actually they have the node 9 has 4 neighbors. So we'll say the degree of node in the degree of node 9 equals to 4, because it has 4 neighbors right there. And the strength is more like the average connectivity power. I take the structural connectivity for example, so you can see the connected fiber number. Maybe you can multiply by the FA. It's kind of a fractional anisotropy value to describe the parameter integrity. But in functional connectivity in fMRI, we will simply use the Pearson correlation coefficient as the measurement. So we can just calculate the average correlation coefficient for these 4 connections between 9 to 8, 9 and 1, 9 and 2, 9 and 3. We have 4 connections right here. We will simply calculate the average number of these 4 connections. Okay. So this is the strength. And another thing is the constant coefficient. We try to estimate the connection between neighbors. For example, again, we take 9 as the example. Now we are not focusing on the 9 per se, but actually we focus on the neighbors of 9. So we take 9 as an example. I can tell that the neighbor is 8, 3, 1, and 2. Now, I'd like to know how many connections between 8, 3, 1, 2. Not the connection between 8 to 9, 1 to 9, 2 to 9, or 3 to 9, but the connection between 8, 3, 1, 2. It's kind of the constant coefficient. So try to estimate how tight connection between a node's neighbor. It's pretty weird, the description, but I'm not focusing on 9, but the connections between his neighbor or between its neighbor is kind of the situation. And finally is the path length, is a separation. How many steps I need to cost when I try to send the information, maybe from 9 to 6. So here is a 1 step, here's a 2 step. So I say the path length from 9 to 6 would be 2 steps or 2 separations. Okay. And it's just four of the a lot of the topological properties. Just take a four simple ones for you to have a general idea about how we summarize the information or how we quantitatively describe the properties of the network. But I only take one node as an example. If you want to summarize the whole brain network, what you should do? Simply, you need to calculate the value for each node and then calculate the average value for all the nodes. It's just the way you summarize the value for the global network. I will go through the details, so don't worry about right now. So I think I spent this some time and try to give you a picture that we will have three different categories to answer the different questions, and it will definitely spend some time that for each analysis it will spend some time. But I think it definitely worth to do because fMRI is a very special data set. For other data set, normally you can only do one thing or two things. But for fMRI, you can do so many different analyses. From the same data set, you can answer so many different questions. And of course, some of the interpretation may highly based on the original hypothesis or original model that you delivered. But anyway, fMRI I think is a beautiful and fascinating data set because you can do so many different analyses. And I think maybe you will enjoy this process after this semester. I think that's all. This is the first week in this semester. And again, I want to emphasize that all the teaching materials you can download from my website, including the handout, the data set, or even the source code. For the MATLAB source code, you can use during the course. Okay, so any question?